All right, here are the couple of problems I didn't quite get around to today in class. But before we do the two problems, I had a very good question after class. Let's see. It was about this idea that the best way to do particle physics is have two masses approaching each other, because then you're in the center of mass frame and all the mass gets converted, or I'm sorry, all the kinetic energy gets converted to internal energy, which creates a lot of mass. Somebody asked, I thought mass was an invariant. How can you go from just these two little masses to a huge amount of mass? So they were mixing up what I said earlier. Remember, invariant and conservation are not the same thing. Remember, conservation is before and after. Mass is not conserved before and after a collision. You can have two little masses before the collision and a big massive masses after the collision. Lorentz invariance means it's the same in two different frames. Right? So totally different. So before the collision, it's two masses with a certain mass in the lab frame. And even if I'm in some other frame moving around, it's still those same two masses. After the collision, the thing explodes into all these exciting masses. All those exciting masses have one total mass in the frame, say, of the center mass. And if I'm moving, they have the same total mass. Right? So the person asking was just mixing those up. And it's so easy to mix them up, I didn't even give them the right answer because I couldn't straighten them out in my head in the few minutes after class. So those are very easy to mix up. Okay, conservation is before or after an event. Invariance is usually referring to, in this class, it's referring to two different frames. All right, anyway, we were working on example 2, and I think we got it started. It was two electrons moving towards each other at 0.6c. 0.6c that way, 0.6c that way. And we're just going to calculate a bunch of stuff about them. I won't lay it out at the beginning. We'll just do it as we go. First, we calculated the kinetic energy of this thing. And let's see, 0.6c we know is 5/4. The gamma is 5/4. So for kinetic energy, gamma minus 1 times mc squared. So for an electron, that's 0.511 MeV per c squared is the mass. And of course, we're going to multiply by c squared. That'll make the c squared go away. So basically, we get 0.128 MeV each. Each one has kinetic energy 0.128. Cool. What's the total? Total energy, well, it's just whatever. You just gamma times that. You take away the minus 1, and let's see. Taking away the minus 1 going to do that much? 0.639 MeV each. I don't feel like if it was, this is, let's see, this is 1 point, oh yeah, it'll make that correct. This is 1.2. 1.25 minus 1 is 0.25. Now we're making it 1.25. So yes, that is correct. Right. So yeah, straightforward use of the formula. That's each. So when you put it all together, the total energy is two of these, and you get 1.278 MeV. Okay, so that's the actual total energy of the whole system. That's just each. Fine. Okay, we did that part. The next thing we could ask is, what is the momentum? All right. So we're actually not going to use the energy-momentum relation because we have the speed. Right? If you have the speed, it's actually quicker just to calculate it with the formula. So gamma 5/4 m 0.511 MeV per c squared times c. All right, so we get 0.383 MeV per c. Each. Right, one of them has that much momentum this way, one of them has that much momentum that way. Therefore, what is the total? P total is 0, because momentum is a vector. So we're sloppy with our vector concepts and notation. We're doing this a lot of times when we say P, we just mean the magnitude. If we're getting the total, of course, you have to sum them as a vector. All right, so it's 0, that's what we expect. We're in the center of mass frame. The two things are moving towards each other That all makes sense. So now I'm going to calculate everything now in the frame of the left electron. Okay, we're changing frames. That's a C. That is an R. There we go. So in the frame of the left electron, let's draw it. Sure. So let's see. This one is at rest, and this one is now coming at us faster than 0.6 C. Galilean would say 1.2 C, but we know that is, of course, not possible. All right. So we're going to keep doing this with velocities, and then we'll compare to the energy-momentum relation. But let's just, for practice, let's figure out how fast that is coming at us. So we have to use the velocity transformations, the relativistic velocity transformations. So we'd say these things were moving, say this one, we would call it ux in that frame, and this is going to be the prime frame. So now it's moving at ux prime. Okay? And we know that the frame we're moving in is now actually 0.6 C that way. So ux prime, let's just find the formula for the velocity transformation. See, the top looked like the classical Galilean part. The top would just be this speed, the original, minus 0.6 C. Right, that's negative because it was moving to the left, minus V, the speed of the frame, minus 0.6 C. That one's negative because there's a negative in the formula. All right. So then underneath goes 1 minus, and then the product of those two velocities, there's the ux in the other frame, minus 0.6 C times V, 0.6 C over C squared. There we go. Okay, so all together, this gives you something like minus 1.2 C, but in the bottom, it's a big positive number, right? So the C's cancel, the bottom, it's fortunately that negative and that negative combined, and you get 1.36, which is guaranteed to drive that one below C, which it has to come out below C. So you get 0.88 C. There you go. So that's how fast this one's going, 0.88 C to the left. So it's negative, I guess. Somewhere there's a negative. There it is, yeah. Negative 0.88 C. Cool. What is gamma for negative 0.88 C? Well, if you keep all the digits, gamma actually comes out pretty nice, 0.88 C, 2.125. All right. So now we're in that frame. Now we know this is at rest. This is moving to the left. Let's calculate some stuff for this example. What did we calculate? Let's see. What do we got? Yeah, we can get the momentum now in this new frame, P prime. All right. So it's just the sum of the momentum of each one, 0. I'll write it down just so you remember. One of them is 0, the one that's not moving. And what's the momentum of the other one plus gamma, 2.1125 times m, 0.511 MeV per C squared times U, which is negative 0.88 C. So we're still keeping motion to the left as negative. So we get negative 0.956 MeV per C. That canceled that, remember momenta are energy over C. Cool. What's the energy? E prime. So the energy in the frame of the left electron, again, let's start out, let's not do it with the energy momentum relation, let's just write it down. What's the total energy of this one? 0.511, because it's not moving, right? And what then would the other one be? It would be gamma, be 2.125 times mc squared, 0.511 MeV. All right, mc squared. You could, if you wanted to think of it as like 0.511 plus 0.511 for this one, plus it's kinetic, and subtract 1 off of that, it's the same thing. Same thing. So what do you get? 1.6 MeV. Total energy. When we don't put a subscript, we mean total energy. If we mean internal energy, then usually it says internal. Okay. What happens when like new particles get made? All right. This one I grabbed from an old textbook. So it looks like you need to know a bunch of particle physics, but I promise you don't. Let's see. We have example 2. We have a pion at rest, and it decays to a muon and an antineutrino. And you need to know a little bit about neutrinos to do this. But if we assigned it, obviously we would tell you what you need to know. All right, I'm going to tell you now. So if we wanted to draw this and write this as a little formula like they would in particle physics, it'd be like that thing's usually negative, I guess. I don't really know. Mu plus nu. So this is the pion, pi, muon, and the muon is the nu symbol. I think that's, I don't know why they use a nu. It'll bar over it too. I think it's because it's an antineutrino. All right, so going in, we need to know, probably want to start, and then the question is, what's the energy of these two when this thing decays? How much energy do they come out with? So the only thing going in that you know is the internal energy of these kinds of particles, right? So a pion is 140. I assume that's MeV per c squared. And a muon is 106. And a neutrino is roughly 0. Okay, so we didn't talk about particles with 0 rest mass in the class yet because the main one is a photon. So photon, we say the energy squared is p squared c squared plus m squared c to the 4th. So for photons, they have 0 rest mass. Right? So basically you just get rid of that and you have E squared equals P squared C squared. That's all you got to do. Neutrino is so light, we'll just pretend it's 0 and treat it like a photon. We didn't get into photons in this chapter because we're going to talk so much about them, more important things about them coming up. So I kind of just skipped that, but that's pretty much all there is to say. Cool. Okay. So that's all we know going in. All right. And the question is, so obviously the tricks are conserve energy. The total energy here equals the total energy here. Conserve momentum. The momentum initially was 0 because the pion was at rest. So the total momentum here has to be 0. So we're just going to use those things to see if we can figure it out. All right. So let's look at the energy, the total energy of the right-hand side. We know the total energy of the left-hand side. It was just a pion at rest. So we can say 140 MeV. mc squared. What does that equal? That equals the energies of these two. Not by squares, it's just E. So what we're going to do is we're going to use the energy momentum relation. We're going to take the square root for the muon, because E squared equals energy momentum relation. So we'll take the square root, and here we'll put the momentum of the muon squared c squared plus the mass of the muon squared c to the 4th. Energy on the left side equals the energy of that plus the energy of this. But remember, it doesn't have any mass. It's just the square root of p squared c squared, so it's just pc. All right, is that right? That is right. Okay, so that's the momentum of the muon, the mass of the muon, and the momentum of the antineutrino. More on it. Cool. Okay, so what are we going to do next? Well, we're going to realize that, remember, we have to conserve momentum. The momentum has to be 0. So the momentum of P mu and P nu are the same magnitude. They are opposite signs. They're vectors. They have to cancel. But when we're doing these formulas, we're usually just dealing with magnitudes. So what we can do is just replace that with mu. One less variable to worry about. So what have we done so far? We've conserved energy. And now we've conserved momentum. So now we can just kind of solve it. Right? We can say 140, everything's in MeV. I'm going to stop writing the MeV. Minus mu(1) momentum c. And then we're going to square both sides. So this is mu(1) momentum squared c squared plus mu(1) mass squared c to the 4th. All right, is that what we're doing? Anything else going away? Oh yeah. What else can we say? Well, what about this? This has no kinetic energy term. This is just the mc squared of a mu(1) squared. 106. So we can replace this with the number 106 squared. Doing some dynamic rewriting and stuff because it's just a problem. Let's see. Then we can FOIL that. FOIL anyone? 140 squared minus 280. Just minus 2 times 140 times the momentum of the mu(1) c plus p mu squared c squared, just square that term, equals the momentum of the mu(1) squared c squared plus 106 squared. And we did all that to make these two go away. Very nice. All right. So now we can basically solve. All we have left is p mu, or the momentum of the mu(1) times c, and then numbers. All right, that goes over there. So then the momentum of the mu(1) times c is just this 140 squared minus 106 squared, all in MeV squared, divided by 280. And then get rid of the c, and the momentum you get is, what is it, 29.9 MeV per c. All that work to get what? To get the momentum of the, there we go. To get the momentum of the mu(1). Okay, very nice. Well, what does that else? What does that tell us? What does that tell us? It also tells us the momentum of the neutrino. It's also 29.9 MeV per c. Why not? Because they're equal and opposite, so their magnitudes are the same. Let's see. What else? Oh, we were asking for the energies, weren't we? How do we get the energies? For the neutrino. Oh yeah. Let's see. So now, okay, we have the momentums, the momenta. Now we need the energies. So for the neutrino, remember, it has no rest mass. So we can use the energy momentum relationship to say, oh, it's just P times C, right? So it's just 29.9. Right? There we go. That is of the neutrino. Because that part is 0, no rest mass. And then we can get the energy of the mu(1) just by conservation of energy at this point. We can say it's 140 MeV minus 29.9. Okay. You say, what about its mass? We're doing total energy. So total energy means we don't subtract out its mass. We're not doing kinetic, we're doing total. So when you subtract those, you get 110.4. So there's the energy of the mu(1). There's the energy of the anti-neutrino. And I guess the one check you could do is it's good that this 110 MeV came out to be bigger than the rest mass, or the rest energy of the mu(1), because otherwise it's not enough energy to make a mu(1). Clearly it was. Okay, so that's how you do sort of these particle disintegration problems. It looks kind of messy, but really all we did was conserve momentum and energy and use the energy momentum relationship a few times.